So we're now talking about the 3D coordinate system. So we are very familiar with the 2D coordinate system, X and Y, the Cartesian plane. Now we're talking about the 3D coordinate system. X, Y, and Z. So here we have three axes. We kind of imagine that Y and Z are in the plane of the screen and that X is kind of pointing out towards us. So that's what this picture is meant to represent. X is coming kind of out of the screen, and Y and Z are the two axes that would be kind of horizontal and vertical in the screen. We can talk about a point in the 3D coordinate space. If we were talking about a point in 2D coordinate space, we would say, how do I get to that point? I go, for instance, along X out to a certain value, and then I turn and I go parallel to Y to get to this point. If I have a point in 3D space, I can imagine going a certain distance out along X, the X-axis, turning and going a distance along Y, or a distance parallel to Y, and then going up parallel to Z to get to my point. So we go along X, we turn and go parallel to Y, and then we go up to get to the correct height. So for instance, if this was 0.3, 2, 4, representing the X, Y, and Z coordinates, we would go out to 3 on X. We would turn and we would go 4 units parallel to Y. So this would be Y equals 4 here. And I don't know why OneNote always loves to turn my 4s into 9s. It just loves doing that. Well, not 4, jumping the gun, 2 on Y. Sorry about that. And then 4 on Z. So this is just a complete analog of the 2D coordinate system, but in 3 dimensions. A little harder to draw because we're trying to represent something that's 3-dimensional in a 2-dimensional screen or piece of paper or something like that. But if we're kind of careful, we can get, I think, reasonable pictures that are reasonably easy to interpret. So we can look at something like, for instance, Z equals 1. In the 3D coordinate system, Z equals 1 is the set of all points that have height 1. So all points that have, say, X, comma, Y, comma, 1. And I see that that is actually going to be a plane. It's going to be a plane that cuts through Z equals 1. It's going to be, in a sense, kind of like a copy of this plane, this Cartesian 2-dimensional plane, where we can go along X and along Y and so on. But the Z coordinate is going to be 1 everywhere there. So if I restrict Z to a certain number and let X and Y be free, that kind of has the feeling of a 2-dimensional plane. One thing that is talked about a lot in engineering, as well as a lot of applied math topics, is degrees of freedom. So how many things can we freely choose? If I'm in a 3D coordinate system like this, I have 3 degrees of freedom. I can pick X, Y, and Z any way that I want, and that's a valid point. If I'm in a 2D coordinate system, I have 2 degrees of freedom. I can pick X and Y any way that I want and get a valid point. If I'm in a structure like this down here, I start off with 3 degrees of freedom. I can pick any point in the 3D plane, and that's a valid point, or the 3D space, and that's a valid point in that space. But then I have one constraint. And it's quite often the case that your degrees of freedom is reduced by 1 for each constraint you have to satisfy. So if I have to satisfy z equals 1, I have initially 3 degrees of freedom, but now I'm restricting the allowable set of points with 1 constraint, so I have 2 degrees of freedom remaining, right? So this feels like that 2D plane. Okay, so what is the distance formula in 3D? The distance between x naught, y naught, z naught, and x1, y1, z1 is just completely analogous to the 2-dimensional distance. X naught minus x1 squared, so the difference in the x's squared, plus the difference in the y squared, plus the difference in the z squared. What's the rationale for this? Well, let's kind of draw out a point, and how about we just consider one point to be the origin and another point to be over here. Draw it in blue. X1, Y1, Z1. What's the distance between these 2 points? That straight line distance. Well, here I see that I can go out along X, go parallel. Oh, that doesn't look very parallel. Go parallel to Y. And then go parallel to Z to get to that point. So if I was taking kind of the so-called taxi cab distance, I would have x1 plus y1 plus z1, but we want a straight line distance. Well, I can look at this point here as kind of an intermediate step, and I can ask, what's the distance from the origin to this point, x1 comma y1 comma 0? I know that distance. That distance squared is x1 minus 0 squared plus y1 minus 0 squared. Right, that's just the Pythagorean theorem. This is x1. This is distance y1. That's a right triangle. So Pythagorean theorem gives me that this green line has distance d, where d squared is x1 squared plus y1 squared. But then from this xy plane, I again make a 90-degree and then go up in the z direction. So this distance that I go up is z1 minus 0, or z1. So now I have 2 sides with lengths d and z1. What's my distance here? My distance is going to be square root of d squared plus z1 squared. So that's where our distance formula comes from. I did it in kind of the special case starting from the origin, but you can see that if we hadn't started from the origin, it would just be a little more subtraction and so on. But they're a very similar idea. So just using the Pythagorean theorem twice, once in the xy plane, and then once we get that straight line distance in the xy plane, then using it in the vertical plane. So let's take an example. Find the distance between the points -1, -1, -1, and -4, -1, +3. So my distance is square root of the difference in the x's. -4 minus a -1 is -3 squared. Distance in the y's is actually 0 squared. Difference in the y's is 0 squared. Difference in the z's, 3 minus a -1, 3 plus 1 is 4 squared. So this is 3 squared plus 4 squared, 25. Square root of 25 is 5. So the distance between these 2 points is 5 units. We can also have equations like, say, y equals x. These can represent geometric structures in 2D space, but also in 3D space. So in 2D space, what do I have? In 2D space, the line, or the equation y equals x, is represented by a line. We kind of know this just from rote memory, but what do we have? We start with a 2D, or 2 degrees of freedom system. We have one constraint. So we're dropped down to 1 degree of freedom. What does it mean to have 1 degree of freedom? It means that you're behaving like a line. You can move one way or the other way, but not in some kind of orthogonal direction. What about in 3-dimensional space? So another way to think about this is, in 2-dimensional space, I can choose initially x and y any way that I want. But then my constraint says, well, y has to equal x. So really, I can only choose points that look like x comma x. Over here, I have a 3-dimensional space. So I start with 3 degrees of freedom. I have to satisfy one constraint. So I expect this to drop me down to 2 degrees of freedom. What does a 2 degree of freedom system look like? Something analogous to a plane is what I would expect. Or another way to look at it is, I can initially pick x, y, and z any way that I want. That would be a valid point in this 3D space, but I have to satisfy this constraint, y equals x. So really, I have to pick points that look like x, comma z. I only have 2 things that I'm free to choose, x and z. Once I choose x and z, my coordinate is completely determined through those choices and this constraint. So what do these points look like? If I chose x equals 0 and z equals 0, or if I chose x equals 0 and z equals 3, or x equals 0 and z equals -10, or if I chose x equals 5, or if I chose x equals -7, right? I get similar things like, so I see that when z equals 0, on this xy plane, I'll try to draw it so it looks decent. When z equals 0 on the xy plane, this kind of flat kind of floor, so to speak, I get a 45-degree line. So this is a line that's 45 degrees from the y-axis and 45 degrees from the x-axis. That's kind of flat. That's perpendicular to z. That's what I would get when z is 0. But z could be 1 or 2 or 3 or -5 or -10. So really, I get a plane that cuts through the z-axis, and that's kind of at this, 45-degree angle between X and Y, or this kind of one-to-one relation between X and Y. So I have 2 degrees of freedom left over, and I get a plane, I get what I would expect. I get a system where I can choose 2 degrees of freedom. Basically, I can choose my height along Z, and then I can also choose one of either X or Y, and then once I've chosen height and one of the others, the third is determined. So what does this equation, x squared plus y squared equals r squared, represent in 2D or 3D? So in 2D, this of course represents a circle with radius r. I start with 2 degrees of freedom. I have one constraint. This drops me down to 1 degree of freedom. 1 degree of freedom is a line. And note that really a circle is qualitatively a line, right? If I'm standing here and I need to stay on the circle, I can only choose to go left or right. I can't choose to go like towards the origin or away from the origin. I can only go one direction or the opposite direction. That's fundamentally a line, right? This is just like a straight line wrapped around itself, wrapped back on itself. So I only have 1 degree of freedom. If I'm standing at a certain point, I can only choose to go left or right. In 3D, I have 3 degrees of freedom, 1 constraint dropping me down to 2 degrees of freedom. I expected this was going to look look something like a plane. If I decide what x is for a given r, if I decide what x is, that tells me what y has to be. But I can still choose z any way that I would like. If I choose z equals 0, I get a circle in the xy plane. But I could have chosen z equals 1 and gotten a circle in this plane that's 1 unit above the xy plane, or z equals -1. So I actually see that I get a cylinder. Right? And a cylinder is, roughly speaking, a plane, right? If I'm standing here, I can choose to go up or down, and I can choose to go left or right. I have 2 dimensions of direction that I can choose. I can move up or down, or I can move left or right. I have 2 degrees of freedom remaining. So this is kind of like a plane, again, wrapped on itself. We might ask, what's the equation of a sphere in 3D space of radius r centered at HKL? So what do I want? I want a point x, or a set of points, x, y, z, such that the distance between x, y, z and HKL remains constant, such that the square root of x minus h squared plus y minus k squared plus z minus l squared, the distance between the 2 points, is a constant r. So what's my constraint? Looks very much like a circle, right? A 2D circle would only have these first 2 terms equals r squared. In 3D, we just pick up this third term, this plus z minus l squared. Note that this equation doesn't have a 2D analog, right? Up here, we were looking at situations where we only had constraints applying to 2 of the variables. So we could say, well, it's not really clear whether that's a 2D. If I just gave you this, it's not clear whether that's a circle in 2D or a cylinder in 3D. I'd have to tell you also what space goes along with it. In this case, I can't interpret this constraint as a constraint related to 2D space, of course, because I have 3 coordinates, X, Y, Z. I suppose I could maybe think that, well, could this be some kind of structure in 4D space or 10D space or something? Well, I suppose so. But for our purposes, we will just be talking about 2D space and 3D space. So just for, to put a constraint out there for this course, we're dealing with 2D and 3D space. But of course, these ideas could be generalized to higher dimensional spaces. Okay. So moving on to section 12.2 on vectors. So definition, a vector is a quantity with both magnitude and direction. So some examples of vectors are things like velocity. So if I say I'm going this fast in this direction, I'm going north at 60 miles an hour, that would be a velocity. That's a vector quantity. It has magnitude, how fast am I going, and direction, which direction am I going. Something like force, if I have a box and I'm pushing with a force, I'm applying a certain amount of effort into that box, but I'm also applying that effort, so to speak, in a certain direction. So force has both a magnitude and direction. Something like acceleration, lots and lots of vector quantities that come up in physics. Note that this is opposed to something like speed, which is what we would call a scalar quantity. So speed is if I get rid of the direction and I just look at the magnitude of the velocity. So speed is like 60 miles an hour, velocity is like 60 miles an hour going north. Now, one note about this is if I imagine that I'm in a one-dimensional space, so let's say I'm just traveling along a certain road, and that's essentially one-dimensional. I can either go that way along the road or I can go backwards along the road. Well, then direction is really only indicated by sign, positive or negative. So then, velocity and speed start to look kind of like one another. But if I imagine that I'm in a 2D space, like, the surface of the earth, like, I don't know, on an ATV or something, where I can turn and go whichever way I want, then just saying I'm going 60 miles an hour is much less clear. Or if I'm in a rocket where I can navigate 3 dimensions, again, saying I'm going 60 miles an hour is much less clear what I mean by that. So vectors have this idea of initial versus terminal points. So let's say that we're looking at a vector v bar. So I usually write it that way. I usually denote it v with kind of an arrow above it. We usually write the arrow just like with one, not usually like that, I guess just because it takes longer to write it that way. And usually in books, you'll see a bold letter representing a vector and a non-bold letter representing a scalar, representing not a vector. But since it's hard to draw bold letters, we put this little arrow over it, and I usually just call it v bar. But vector v has an initial point and a terminal point. It has an initial point It's usually represented by a dot. It has a terminal point that's usually represented by an arrow. And then we connect the dot to that arrow. Sometimes the points have names. We can call maybe the initial point A and the terminal point B. And we might say something like V bar equals AB bar. So sometimes we'll represent this vector that way by stating the initial and terminal points A and B with a bar over it. So the vector going from A to B. So what does it mean for two vectors to be equal? This is one of kind of the strangest, but also the most useful ideas in vectors, is that two vectors are equal if they have the same magnitude and direction. Note that our discussion of equality said nothing about the same initial and terminal points. So if I come down here and I have a vector u bar, this has, I mean, at least to my ability to draw, the same direction, the same magnitude. U bar equals V bar, even though they start and end at different points on the screen. But they're considered to be equal vectors. If I said that this went from C to D, I could say that C D bar equals AB bar, because the two vectors have the same magnitude and direction. Even though one starts at A and ends at B, and another starts at C and ends at D, they start and end at different points, but same magnitude and direction, the two vectors are equal. So vector addition. How do we add two vectors? Say U bar plus V bar, not necessarily the same U and V is up there. So let's consider a vector U and a vector V. How would I add these together? Well, U plus V, what I would do is I would start by taking U. And I want to add V to it. So I would put the initial point of V at the terminal point of U. So let's say U bar goes from C to D, and then V bar might go from D to E. U bar plus V bar, what I think about is I think of traveling along U bar, then traveling parallel to V bar. That gives me an overall net effect of if I had traveled along this vector, going directly from C to E. So I could go C to D to E, but I could have also gotten from that initial, kind of the initial point to the terminal point, from here to here, by just going directly from C to E. Something I might notice is that I could have also started at C, and I could have gone along V bar this way, and then U. I would have gotten to the same point. If I started at C, I would have gotten to E. So U bar plus V bar is the same as V bar plus U bar. This is sometimes called the parallelogram rule, because V then U versus U then V kind of makes a parallelogram, and you're just going from one corner to the other. it doesn't matter which path you go along, whether you go along V first, then U, or vice versa. Where is this helpful? Well, for things like, when you apply force to an object, if two different forces are being applied to the object, maybe different magnitudes, different directions, how do you get the resultant force, the kind of net force that's applied to that object? So, and another way to say this is the vector addition is commutative. Right? We're in this new algebraic structure. We have kind of seemingly very strange ideas of equality and so on. We're not really sure, right? We have lots of algebraic structures that apply to things like scalars, like just numbers. We're not sure to what extent those apply to these vectors, but we see here we have commutativity of addition between vectors. So that's nice, right? That's a property that now we understand that we can use when it benefits us. What about scalar multiplication? Well, if we have C, a real number, bigger than 0, then C multiplied by U bar, which I'm just going to write as C U bar. I don't want to put the dot there. We'll see why later. There's actually something called the dot product, and we don't want to mistakenly think that this is the dot product. But so I'll just write it as C U bar, and I'll omit the dot or any notion of times or anything. I'll just put C U bar. We have an understanding that C is a real number because C does not have a bar over it. This is a vector. So if I multiply a vector by a scalar, I get a vector. It has the same direction when C is positive, and its magnitude is multiplied by C. So the magnitude of this new vector, maybe we can call it W bar. So the magnitude of W bar equals C times the magnitude of U bar. If C is less than 0, we still get, for CU bar, we still get a vector. Instead of the same direction, it's in the opposite direction. In other words, initial and terminal point swap places, make the initial point the previous terminal point and vice versa. And the magnitude is multiplied by the absolute value of C. So if C is 3, 3U bar just takes the vector U and stretches it by a factor of 3, makes it 3 times as long. It keeps it in the same direction. Negative 3U bar takes that vector 3U bar and just flips the initial and terminal points. So if I have U bar, see if I can do this. So this would be, for instance, 2U bar, right? U bar plus U bar be 2U bar. It's in the same direction, but just stretched by a factor of 2. So I could just draw the vector like that. If I had negative 2u bar, so if I had negative 2u bar, what does that change? That changes the initial and terminal points. So I make 2u bar and then I just swap the initial and terminal points. If I had a half u bar, I would cut my magnitude in half, and that would compress my vector. So we see that scalar multiplication stretches or compresses the vector, and if the scalar is negative, it can flip the initial and terminal points. So kind of what we do is we keep the same direction, roughly speaking, we just change the magnitude. And if we interpret negative magnitude as just meaning initial and terminal points going the opposite direction, then we're just kind of changing the magnitude, but keeping the same direction, at least in kind of a loose sense of same direction. Right, we have the same slope, so to speak, even though we might be pointed kind of backwards. So what about vector subtraction? What about the difference of two vectors? What does it mean to have u bar minus v bar? Well, we always define things like subtraction in relation to addition or division in relation to multiplication. So let's say u bar minus v bar is w bar. So w bar is what I'm interested in. But I can say that u bar is w bar plus v bar. So what does that tell me? If I have u bar, let's say it looks like this. And if I have v bar that, I don't know, let's say it looks like that. I want to find w bar, I want to find a w bar so that w bar plus v bar equals u bar. I want to move my u label over here to below. There we go. Okay, so I want w bar plus v bar equals u bar. This tells me that I want the terminal point of v bar to be at the terminal point of u bar. So let me try to make that happen. So I want the terminal point of v bar. Let me also switch my, switch my v bar label to the other side. See if I can get these. I want my terminal point of v bar to be at the terminal point of u bar. And then that tells me what w bar has to be, right? So I just kind of drew an example over there, but that tells me that w bar has to have the same initial point as u bar for this addition. So what is w bar equals u bar minus v bar? Well, minus v bar points this way, right? So we can see that u bar plus negative v bar gives me W bar. So if I had U bar like that, if I had V bar like that, then W bar is going to look like this. Or U bar minus V bar is going to look like this. Note that subtraction is not commutative, right? U bar minus V bar, so going here, then this way, is not the same as V bar minus U bar, which would be going this way, then that way. That would swap the initial and terminal points of W bar. So V bar minus U bar we do see is negative W bar. It's kind of the same looking vector, but with the initial and terminal points swapped. So, okay, so another definition. Components of vectors. If a vector u were positioned with initial point at the origin, then the coordinates, the xy coordinates or xyz coordinates of its terminal point are called the components of u. So in other words, I'll do this in 2D. So if I have a vector u bar like this, if I put the initial point at the origin, and maybe the terminal point ends up at 2, 2, then I'd say the components of u bar are 2 and 2, or typically I would just say u bar equals, with angle brackets, 2, 2. You can also see this written as square brackets, and occasionally you also see it written as parentheses. So, but the context is going to tell you whether something like this, whether that represents an interval or a point in space, or whether it's representing the coordinates of a vector. So just kind of depending on the context, linear algebra a lot of times uses the square brackets when you're in that context. Things like physics and the calculus side of things more often uses the angle brackets, because in calculus, we talk a lot more about intervals of the real line, where square brackets 2, 2 or parentheses 2, 2 kind of looks like intervals on a real line, so it can get a little more easily confused. But in linear algebra, you're not talking about intervals so much, so a lot of times you'll use square brackets in linear algebra. You sometimes also see it just written as like 2, 2 like that without a comma. So it's very context dependent where you see which notation. Okay, so some properties. We have commutativity of vector addition. We have a zero element. The zero vector is the vector that has magnitude 0. And if it has magnitude 0, it doesn't really have a direction. So if I add the 0 vector to a vector, I just get the original vector back. 0 is the identity vector. The 0 vector has coordinates or components 0, 0, has coordinates of the terminal point that are the same as the initial point. We have scalar distributivity. Scalars distribute multiplicatively over sums of vectors. We have scalar associativity. So scalar CD times U bar is C times DU bar. Something to note is we have not said anything about vector times vector, and that's really where dot product and cross product come in. It's not so easy to say what we mean by the product of two vectors. The sum of two vectors had kind of a sensible definition. Product of two vectors maybe needs a little more treatment. The magnitude of a vector, aka the length of the vector, is square root of the sum of the squares of its components, or it is when we position the initial point at the origin, we have a terminal point that is some point in either 2D space or 3D space. It's just the distance from the origin to that point in that 2D or 3D space. So we can think of it either way. We can think of it as the distance between the initial and terminal point, or we can think of it as the square root of the sum of the squares of the components. We say that a vector is a unit vector if its length, if its magnitude is 1. Unit vectors are quite important for a lot of the things in Calc 3. So being able to create a unit vector, or in other words, being able to create a vector that's in the same direction as the original one, but has length 1 is important. So for any vector that is not the zero vector, that's not the identity vector, we can create a unit vector in the same direction by taking the original vector and dividing it by its length, essentially multiplying by a number, by a scalar that is 1 over length v. So if I take u bar as 1 over length v bar, which is just a scalar, that's a number, times the vector v bar, u bar is a unit vector pointing in the same direction as v bar. We also have standard basis vectors. I'll blow this up a little. These are hats. So I hat, j hat, k hat is how we denote the standard basis vectors. I hat is 1, 0, 0, j hat 0, 1, 0, k hat 0, 0, 1. These are the unit vectors that are pointing in the direction of the kind of standard positive axes. And then last question is, consider the vector with these components, 10, negative pi, 1/2. Can we write this in terms of the standard basis vectors? And the answer is yes. U bar is 10 I hat minus pi j hat plus 1/2 k hat. So this is just saying go in the x direction 10 units, go in the y direction minus pi units, go in the z direction 1/2 of a unit. So that's the equivalent in terms of the standard basis vectors. And yes, the process can be generalized. If u bar is u1, comma u2, comma u3, u bar can also be written as u1 I hat plus u2 j hat plus u3 k hat. And a lot of times this is very helpful to do for calculations and understanding, is to write it in terms of the standard basis vectors. And in linear algebra, you'll see that you can use different bases. Sometimes a different basis is more helpful in a certain situation. Okay, so